Hey guys, let's do some Bragg diffraction. So here's the setup. We have a source. It's incident on a crystal with plane separation, D0. Incident angle, scattering angle, detector, one wavelength, Bragg condition. This is for inelastic scattering. With elastic scattering, the magnitudes of the k vectors are equal, so the angles are equal. First order scattering means we have a difference between the incident waves of just one wavelength, and then the distance, I didn't draw it here, but there's one wavelength here, that's why we have this 2 down here. So for n equals 1, this Bragg condition is a first order condition. And we end up with this delta k. The difference between the two k vectors is always perpendicular to our plane. Delta k for the first order is the smallest. Every higher order, the delta k grows. So it's this first order that's the critical value, and in fact it determines the boundary points of the first Brouwan zone. So our angle theta is a function of the order, or vice versa. So for alternate directions, we have all the same mechanisms. We have first order, second order, whatever. Because for alternate directions we still have the same wavelength, then the Bragg condition has to hold for any direction that we're talking about. So that means we have to have different angles and different separations between the planes. As such, if we're talking about different directions, we have to define the directions in order to define the separation. And same with the perpendicular reciprocal lattice vector. So we need to determine how to find these values, these Miller indices. First, we need to talk about the Bragg lattice, which is a tiling of the smallest unit cell, where these vectors are a basis to locate all of the sites within one unit cell. Then we can translate this unit cell anywhere we want in any direction. I've only shown you translation vectors going up for some reason here, but you can go down or whichever direction, as long as you're talking about a Bragg lattice. It's an infinitely tileable pattern. And in order for this to happen, these translation vectors have to have integer coefficients. And the basis doesn't have to have magnitude 1. So to find the Miller indices, we find the intercepts of the plane, whichever plane we're talking about. So let's do this one, for example. This prime plane. Let's talk about this plane here. Well, you look for the closest site to the plane that isn't in the plane. That is an integer or more distance away from a site in the plane. So this guy is a perfect candidate because it's one integer away in terms of the basis vectors. Recall that this basis vector here in the x direction is a1, and this is a minus a1 right here. So then I get a minus a1. That's in the x direction. And then if I go 2 up, that's my y-intercept, so I get a 2. And z-intercept is an infinity because it never intercepts. So then I do 1 over those values. So I have a 1 over -1, 1 over 2, 1 over infinity. I clear the fractions so that HKL are the smallest possible integers. And that's what you get. -2, that's how you write it, 1, 0 for this plane here. Notice that the separation between these guys, as it increases, going from double prime, prime, then the reciprocal lattice vectors decrease. So then they must be inversely proportional. The higher order reciprocal lattice vectors determine a plane, a distance between planes, but notice that this is 2 times this. So this is 1/2 of this. So look at this, for example, this D0. Then if I'm talking about the second order delta K, that would define a plane that's right in the middle here, which doesn't exist. But still, delta K is important. It's valid. It's just that we have to fold the values for these larger delta Ks into the first Brouillon zone defined by the first order delta Ks. So how do we find the delta Ks and the HKLs that give us our distance between the planes? We have a source here. Source is sourcing a plane wave. Let's just talk about one plane wave at a time. And it's defined by this R from this RS vector from this arbitrarily chosen origin. I could have put this origin anywhere. And this would have been a plane wave with respect to that origin. But all we care about is the plane wave as it travels along this K vector, and that's determined by this vector R. So then the incident plane wave on our sample is correctly defined no matter where I put the origin, because this is R here. So once it is scattered, this family of plane waves coming along here is scattered, and what is scattered are scattered from individual sites. So it's actually spherical waves that are scattered. That's what we have here. The detector sees a superposition of spherical waves, which of course by Huygens principle ends up being plane waves anyway, but if we look at one at a time, then we have these 1 over r prime, where this r prime is along the k prime vector. So the important thing is that this 1 over r prime can be grouped into an amplitude here of all the terms in this spherical plane wave that don't depend on little r. Even though r prime does depend on little r, we're using what's called the paraxial approximation that says even as this little r changes, it doesn't change much for this distance here. So r prime is essentially constant with respect to r. the praxial approximation is only valid for amplitudes, not for phases. So the phase here is very sensitive to that R, so it has to remain. So all of the terms that aren't dependent on R are in this E0, and we end up with just this simplified term here. So if we add up all of these plane waves to get the total scattering amplitude, that will give us all of our constructive and destructive terms in this integral. And we've said that the density of sites is periodic. Well, it's a crystal, so that's the definition of a crystal. So that means that the density has to be periodic. We have to enforce, that's what this is, we're enforcing the periodicity with respect to these translation vectors. So in order for this to be true, then if I replace R by R plus RT, then G dot RT must be an integer multiple of 2 pi. So G, if we use a basis, BI, G is the span of that basis restricted to integer coefficients. Because RT, the real space translation vectors, are also restricted to integer coefficients. So for this to be true, then we must restrict our coefficients to integers here, and the bases must multiply together so that we get this. And in order to get that, then we use a basis that is built from the direct basis, the real space basis. So our reciprocal basis is built from our direct space basis, and that enforces this condition and this condition. So knowing that we have these bases, then it's straightforward to show this relationship here. And in particular, this allows us to find our lattice constant, A, for a cubic lattice. All right, I think that's it.